Imagine two cities each with skyscrapers, highways, and tens of millions of people slowly drifting toward one another until, eventually, their downtowns begin to overlap. Now swap the cities for entire galaxies, huge collections of stars, gas, dust, and dark matter, and replace the skyscrapers with a monster at each center. A supermassive black hole, weighing millions to billions of times the mass of our Sun. When those two central monsters meet, what happens is one of the most dramatic events the universe can stage. Spacetime itself is ripped, stretched, and set ringing. Vast amounts of energy are released in the form of gravitational waves, and an even larger black hole is born. But the story is not a single explosive moment. It's a long, multi-stage process shaped by gravity, gas, stars, and time. Start at the beginning, galaxies merge. Over cosmic time, gravity pulls galaxies toward one another. When they collide, the stars inside mostly pass by one another because stars are tiny and widely separated compared to the distances between them. Direct star-on-star collisions are extremely rare. But the big players, the supermassive black holes, SMBHs, feel the effects differently. Each SMBH sits at the center of its galaxy, surrounded by stars and gas. As the galaxies interleave, the black holes find themselves in a new, common gravitational field and begin to sink toward the merged center. This sinking is driven by a process called dynamical friction. As a massive object moves through a sea of less massive objects, stars, dark matter, gas, it gravitationally focuses them, creating a wake behind it. That wake pulls back on the black hole, stealing kinetic energy and causing it to spiral inward. Over millions to billions of years, the two black holes close the distance between them and form a bound system, a binary. Once bound, the binary slowly tightens its grip. At first, dynamical friction and interactions with the surrounding stars and gas dominate the energy loss. The binary loses orbital energy by slinging away individual stars in three-body interactions and by transferring momentum into the gas. Each time a star passes near the binary, it can get a kick and be thrown into a different orbit or ejected from the system, carrying away energy and letting the black holes move closer. This process is messy and can be slow. For a long time, astrophysicists worried about the so-called final parsec problem. Once a supermassive binary gets to within about a parsec, 3.26 light-years, there might not be enough stars on the right trajectories to keep removing energy efficiently, potentially stalling the merger. Real galaxies are not perfect, symmetrical systems. They have gas, irregular orbits, triaxial shapes, and other complexities. And these effects generally help the binary keep shrinking until gravity itself takes over. When the separation becomes small enough, typically milliparsecs or less, depending on the masses, the dominant mechanism for energy loss switches from dynamical friction and stellar interactions to gravitational radiation. This is the phase where the black holes spiral inward rapidly, emitting gravitational waves, ripples in spacetime that travel outward at the speed of light. A useful way to picture gravitational waves is to imagine dropping a stone in a pond. The ripples spread out from the impact. That analogy breaks down in details, but it captures the idea that the motion of massive objects creates disturbances that propagate outward. In Einstein's theory, masses and their accelerations change the curvature of spacetime, and those changes carry energy away. As the two supermassive black holes close in, their orbital speed grows. In the finest moments before merger, they orbit each other at a significant fraction of the speed of light. The gravitational waves produced during these last orbits are extremely strong, and they carry away energy and angular momentum. The waves are most intense during a brief final phase. Inspiral, the slow inward decay; plunge, the rapid final approach; merger, when two horizons join; and ringdown, the final newly formed black hole settling down. The merger is a non-linear, deeply relativistic event in which spacetime is being contorted in ways only general relativity can describe. Numerical relativity, solving Einstein's equations on supercomputers, has been essential to understanding the precise sequence of these last moments. What does the physics do to the black holes themselves? They don't explode in the classical sense. Black holes have an event horizon, a boundary beyond which nothing, not even light, can escape. When two black holes approach and merge, their horizons eventually touch and fuse into a single, larger horizon. The end product is a single black hole characterized, according to the no-hair theorem, by just a few numbers. Its mass, its spin, how fast it's rotating, and essentially zero electric charge for astrophysical cases. All the messy details of the initial black hole's shapes and orientations get radiated away in the ringed-on stage as gravitational waves, analogous to how a bell's complex vibrations damp down until you hear a single, ringing tone. A remarkable fact is how much energy can be liberated in that short endgame. For black holes of comparable mass, a few percent, sometimes more, of the total mass energy can be emitted as gravitational waves. That sounds small until you translate it into familiar terms. For 2 billion solar mass black holes, even 1% of the total mass converted to energy is an astronomical amount. The peak power output in gravitational waves during the coalescence of massive black holes can exceed by many orders of magnitude the combined luminosity of all the stars in the observable universe, if we count energy radiated per unit time. But because this enormous power is emitted mostly in gravitational waves, which interact extremely weakly with matter, the universe doesn't suddenly light up. Instead, spacetime itself gets disturbed, and those disturbances pass through everything almost unimpeded. Gravitational waves carry not just energy, but also momentum and angular momentum. Because of asymmetries in the masses or spins of the merging holes, the waves can be emitted unevenly in different directions. That anisotropic emission gives a recoil, or kick, to the newly formed black hole. Depending on the mass ratio and the orientation and magnitude of the pre-merger spins, this kick can range from tens to thousands of kilometers per second. For many galaxies, a kick of a few hundred km/s is not enough to escape a massive galaxy's gravitational pull. But for smaller galaxies, a kick of a few thousand km/s could launch the newly formed black hole entirely out of the galaxy into intergalactic space. A kicked black hole might carry along a shroud of gas and stars, leaving observable signatures, a displaced active galactic nucleus, AGN, a bright emission line with velocity shifts, or stars moving unusually fast near the galaxy center. Whether or not there's visible fireworks depends on the environment. If the binary sits in a gas-rich center, there's likely a circumbinary disk, a larger, donut-shaped reservoir of gas surrounding the two black holes. That disk often has a gap carved out by the binary, and each black hole may host its own mini-disk fed by streams crossing the gap. As the binary tightens, the gas dynamics become complex. The interaction with the binary can modulate the accretion flow, producing periodic variations in brightness that might be detectable in electromagnetic observations. When the black holes finally merge, the sudden change in the central gravitational potential, combined with the energy deposited by the merger and the possible recoil, can shock the surrounding gas. That can produce flares in X-rays, ultraviolet and optical light, or even change the direction and power of relativistic jets if the black hole is actively launching them. So under the right conditions, a black hole merger could be both a gravitational wave event and an electromagnetic event, a multi-messenger spectacle. Not all mergers will have easily detectable electromagnetic counterparts, though. If the system is gas-poor, there's little to light up. But even in gas-rich cases, the timing and nature of any electromagnetic signals are complicated. Some models predict a bright precursor as the binary clears its environment, others expect a flare at the moment of merger, and still others suggest a delayed afterglow as the disturbed disk resettles. Observationally, astronomers are looking for hints, periodic variability in quasars that could indicate a binary, transient flares or shifted emission lines suggesting a recoil, or spatially offset AGN that imply a wandering black hole. Candidates exist. One famous example is the blazar OJ 287, which shows regular outbursts that some models interpret as a smaller black hole punching through the accretion disk of a larger companion every dozen years or so. But confirming these interpretations is difficult. That's why combining gravitational wave detections with electromagnetic observations is so valuable. The waves give the merger's timing and masses, while light reveals the environment and energetic aftermath. Detection strategy is key because supermassive black hole mergers don't produce the same kind of high-frequency gravitational waves that ground-based detectors such as LIGO and Virgo pick up. Those instruments are tuned to frequencies of tens to thousands of hertz, perfect for stellar mass black hole mergers and neutron star collisions. Supermassive black hole binaries, on the other hand, emit at much lower frequencies, from nanohertz to millihertz, depending on the masses and the separation. This means different instruments are needed. For sources in the millihertz band, roughly 10⁻⁴ to 10⁻⁻⁴ Hz, a space-based observatory like LISA, Laser Interferometer Space Antenna, is ideal. LISA, planned to launch in the 2030s, will consist of 3 spacecraft forming a giant triangle millions of kilometers on a side, measuring tiny changes in distances caused by passing gravitational waves. LISA will be sensitive to mergers of black holes, with masses around 10⁴ to 10⁷ solar masses, and will be able to observe the inspiral over months to years, offering precise measurements of masses, spins, and sky localization, so astronomers can point electromagnetic telescopes at the right patch of sky. At even lower frequencies, nanohertz, corresponding to periods of years, we rely on a different tool, pulsar timing arrays, PTAs. Pulsars are extremely regular spinning neutron stars that emit beams of radio waves like cosmic lighthouses. By timing the arrival of pulses from a network of millisecond pulsars across the sky, astronomers can detect correlated variations caused by passing gravitational waves. Supermassive black hole binaries in the final stages of inspiral, especially the most massive ones, millions to billions of solar masses, are expected to create a background hum of low-frequency gravitational waves. Recently, PTA collaborations, Nanograv in North America, the European Pulsar Timing Array, and others, reported evidence for a common spectrum signal across multiple pulsars that is consistent with a gravitational wave background. If confirmed as gravitational waves, this would be the first detection of the collective signal from many distant supermassive binaries. In time, individual loud binaries may be resolved, giving us a new way to watch these titanic mergers unfold. The final merged black hole's properties, mass, spin, and recoil, depend on the masses and spins of the progenitors and the orientation of those spins relative to the orbit. If both black holes have high spins aligned with the orbital axis, the final hole tends to have a higher spin. If spins are misaligned or oppositely oriented, the outcome can be a slower spin and a larger gravitational recoil. If one black hole is much more massive than the other, the result is more like the larger object just swallowing the smaller with less dramatic wave emission. The spin of the final hole matters for the environment too. It determines how effectively magnetic fields can extract rotational energy to power jets via mechanisms like the Blandford-Zienagic process. So a merger can turn a quiescent black hole into a powerful jet engine, or reorient existing jets, producing observable changes in radio and X-ray emission. The merger process also reshapes the population of stars near the center. As the binary hardens by ejecting stars, it carves out a low-density core in the galaxy's stellar distribution. Observations of massive elliptical galaxies often reveal these cores, regions where the star density is lower than expected, and this is interpreted as the aftermath of one or more supermassive black hole mergers. The amount of stellar mass missing, sometimes called the mass deficit, offers clues to the merger history. Each binary phase can eject a substantial mass in stars as the black holes lose energy. Repeated mergers over the history of a galaxy can create especially large cores. Thinking about timescales helps ground the drama. Galaxy mergers take hundreds of millions to billions of years from the first close passage to final coalescence of the central black holes. The final gravitational wave-dominated inspiral, by contrast, can be much quicker. The last few thousand orbits might take years or months for SMBHs accessible to LISA, while for the most massive pairs observed by PTAs, the final phase could last centuries to millennia in human terms. From a human perspective, the entire merger is slow and stately. From a cosmic one, those last minutes or hours of the plunge and merger are a sudden, energetic finale. For the gravitational wave detectors, being able to observe the inspiral over extended periods is a huge advantage. It allows precise tracking of the binary's parameters and timing, enabling alerts to telescopes for coordinated electromagnetic follow-up. A merged supermassive black hole can have profound long-term consequences for its galaxy. If the merger triggers or enhances accretion, it can ignite an active galactic nucleus, a quasar, that bathes the galaxy in intense radiation and powerful winds. Those outflows can heat and expel gas, suppressing star formation in a process called AGN feedback. This feedback is thought to help regulate galaxy growth and may explain why the most massive galaxies host very old stellar populations. Their gas was expelled or heated long ago, shutting down star formation. So a black hole merger is not just a local event confined to the very center. It can influence the evolution of the whole galaxy over many millions of years. There are other, subtler possibilities. If the merged hole receives a significant kick, an active black hole kicked out of the center may carry its accretion disk and broad emission line region with it, producing a luminous AGN offset from the galaxy nucleus. Observers might detect emission lines shifted in velocity, or a displaced radio or X-ray source. If the kicked black hole escapes entirely into intergalactic space, it could continue to shine as a hypercompact stellar system with a tiny cluster of bound stars, or as a lone accreting object if it encountered enough gas. Alternatively, a recoiling black hole that doesn't escape may oscillate through the galaxy center for tens to hundreds of millions of years before settling down, stirring stars and gas as it goes. The gravitational wave signals themselves carry deep tests of fundamental physics. By measuring the wave's shapes and polarizations, we can test general relativity in the strong field, highly dynamical regime, exactly the conditions near merging black holes. The ringed-on phase is particularly valuable. It encodes the quasi-normal modes, the characteristic frequencies at which the new black hole vibrates. Measuring multiple ringed-on modes could allow a direct test of the no-hair theorem. In GR, those modes are determined only by mass and spin. Any deviation could hint at new physics or exotic alternatives to black holes. Precision gravitational wave astronomy with instruments like LISA and PTAs could open that door. There's a human side to all this. By watching black hole mergers, astronomers can trace the growth history of black holes and galaxies across cosmic time. Are the biggest black holes built up primarily by accretion of gas, by repeated mergers with other black holes, or a mix of both? Gravitational wave detections will reveal how common mergers are, their typical mass ratios and spin orientations, and how these properties evolve with redshift. That informs models of galaxy formation and the coevolution of galaxies and their central black holes, a central question in modern astrophysics. Simulations and theoretical modeling give us rough numbers and vivid predictions. For two equal-mass black holes with moderate spins, the merger can radiate away on the order of a few % of the system's rest mass as gravitational waves. For example, if two 100 million solar mass black holes merged and radiated 1% of their mass energy, that's equivalent to converting a million solar masses entirely into energy, an almost unimaginable amount. The resulting black hole would be slightly lighter than the total pre-merger mass, because some mass went into the waves. The remnant spin might be in the ballpark of 0.7 in dimensionless units, where 1 is the maximal spin allowed by general relativity, but a wide range is possible depending on initial spins and the orbital geometry. The details of the electromagnetic signature depend on gas density, magnetic fields, and how the disk behaves at small scales. If a substantial circumbinary disk is present, its inner edge may follow the binary inwards until gravitational wave emission dominates. As the final plunge occurs, gas streams can crash onto the remnant, leading to shocks and sudden brightening. If the black hole's power jets, the merger can either strengthen or reorient the jet. In some simulations, a sudden realignment of the spin axis due to merger can produce a kink in the jet direction, leaving distinctive radiomorphology. Observers have found galaxies with strangely bent or double-lobed jets that might be fossil evidence of past mergers. These relics give clues to a dynamic, merger-rich history. Looking beyond individual galaxies, the universe contains an enormous population of supermassive black hole binaries at different stages of inspiral. Many of them, especially the heaviest and those in dense environments, will produce a stochastic gravitational wave background observable by PTAs. Other, rarer events, closer, brighter mergers, may stand out as resolvable sources. When LISA flies, it will be able to pick up mergers across much of cosmic history, potentially observing the formation of billion solar mass black holes in the early universe and testing models of how the first massive black holes grew so large so quickly. One of the most exciting prospects is multi-messenger astronomy, detecting both the gravitational waves and the light from the same event. Having the gravitational wave signal fixes the merger's time and gives an independent distance measurement, a standard siren, while electromagnetic observations provide redshift and detailed properties of the surrounding matter. Combined, these measurements allow a direct way to probe the expansion of the universe by linking distance to redshift, without relying on cosmic ladders like supernovae. For SMBH mergers, if we can get a precise sky position from the gravitational waves, LISA promises good localization for many sources, and find the host galaxy and its redshift, we could measure cosmological parameters in a new, independent way. There are also intriguing, more speculative ideas. Some theories propose that mergers of extremely massive black holes could momentarily create conditions for exotic physics, perhaps triggering bursts of particle production or serving as laboratories for high-energy processes. While there is no confirmed evidence for new physics, gravitational wave observations expand the range over which we can test fundamental laws. It's worth returning to a basic point. Despite the dramatic language scientists use, collision, cataclysm, merger of titans, two black holes coming together is largely an act of gravity sweeping the deck. Much of the visible structure of the galaxies, the stars and gas, remain intact on large scales. Planetary systems are unlikely to be directly torn apart by the passage of the black holes. Distances are vast. The effects are concentrated in the galactic nucleus, where stars can be flung out, gas can be shocked, and the black hole's activity can heat or expel the galactic fuel for new star formation. So the merger reshapes the center and the evolution of the galaxy over long timescales, rather than causing a catastrophic explosion across the whole system. From a theoretical and observational point of view, merging supermassive black holes are a gold mine. They test gravity where it's strongest, tell us how black holes and galaxies co-evolve, and offer rare opportunities for coordinated observations across the electromagnetic spectrum and gravitational wave channels. We're at the beginning of an era where instruments like LISA and the ever-improving pulsar timing arrays will let us hear these mergers directly, complementing what we already see with telescopes. Each detection will be a window into a violent, hidden process shaping the structures of the cosmos. We can imagine a specific scenario to anchor the ideas. Picture two large spiral galaxies, each with a central black hole of, say, several hundred million solar masses. They pass close enough to become gravitationally bound, and over a period of a few hundred million years, their stellar halos and gas flows intermix. The black holes sink to a common center, forming a binary separated by a few light years. Over tens to hundreds of millions of years, the binary ejects stars and interacts with gas, slowly tightening. As the separation drops below a parsec, gravitational waves begin to play a role, and over the final thousands of orbits, perhaps spreading across a few decades or centuries, the wave signal strengthens. In the final months to years, for masses LISA will target, the waves sweep upward in frequency and amplitude until the horizons touch. In that last moment, the gravitational waveform peaks and then damps as the remnant settles. Meanwhile, if gas is present, the surrounding disk may light up, jets may flare or shift, and the merged black hole may receive a kick and wander off-center for a while. Then, in the longer view, the galaxy might experience a burst of AGN feedback, clearing out gas and slowing further star formation, leaving traces in the galaxy's structure that future astronomers can read. This is a story where different parts of physics come together. Newtonian gravity governs the early sinking and interactions with stars. Hydrodynamics controls the behavior of the gas and the electromagnetic output. Einstein's general relativity rules the final inspiral, merger and gravitational wave production. It's an interplay of scales, from the global evolution of galaxies over hundreds of millions of years, down to the last few minutes when relativistic gravity dominates. The universe gives us these grand laboratories, and with the right instruments and careful analysis, we can watch them, measure them, and learn from them. Detecting and interpreting these events is a technical challenge. Pulsar timing arrays require monitoring dozens to hundreds of the most stable millisecond pulsars for many years, looking for correlated deviations in arrival times on the order of tens to hundreds of nanoseconds. Space-based detectors like LISA require exquisite control of spacecraft and laser links spanning millions of kilometers, able to detect changes in distance smaller than an atom over those vast baselines. Both approaches demand patience, precision, and international collaboration. But the payoff is huge, a new sense for how the universe's heaviest objects behave in their most extreme encounters. There are still uncertainties and open questions. How often do supermassive black holes actually merge? How efficiently do they pair and harden in different galactic environments? Do many mergers stall, or does gas and galaxy asymmetry always drive them to coalescence? What is the distribution of spins in merging SMBHS, and how does that affect the demographics of recoils and the growth of spin through cosmic time? As more gravitational wave data arrive, especially across different frequency bands, we'll start answering these questions with real statistics rather than theory alone. In short, when two supermassive black holes merge, the universe stages an epic but highly relativistic dance. Spacetime is sculpted into powerful ripples. Energy and momentum are flung into the cosmos via gravitational waves, and a single, mightier black hole emerges. The surrounding stars and gas are stirred, sometimes violently. Jets may brighten or realign, and the galaxy's future can be altered by the radiation and feedback that follow. Observers watching with telescopes and gravitational wave detectors are now beginning to pick up the chorus. A deep, low-frequency hum from many mergers, and in time, individual songs from especially loud or nearby binaries. Each observation will tell a piece of the story of how galaxies and their central monsters grow, interact, and shape the universe we see. We've already walked through the broad sweep of how two supermassive black holes find each other, dance, and finally fuse. The next question is practical and a little bit thrilling. What would an actual observation look like, and what can we learn from watching one of these mergers in real time? Think of this as both a detective story and a live broadcast. Astronomy is shifting from purely looking at snapshots of the past to listening in on dynamic events as they unfold. For supermassive black hole mergers, that means combining long-term monitoring, clever alerts, and multi-wavelength follow-up to catch as much of the story as possible. Start with the warning signs. For some mergers that LISA will be able to detect, the inspiral phase could be observed for months or even years before the final coalescence. That's because LISA will be sensitive to the lower frequency gravitational waves produced by relatively wide binaries of massive black holes. During this phase, The frequency and amplitude of the waves slowly climb, a chirp that encodes the masses and spins of the two holes and the distance to the system. Crucially, because the signal accumulates over many cycles, LISA can measure parameters with impressive precision and gradually narrow down the sky location. Months ahead of merger, astronomers may already have a patch of sky to watch, and that patch will continue to shrink as the binary moves toward the final plunge. Imagine receiving a weeks to months notice that a billion solar mass binary in a particular region of the sky is about to merge. That gives telescopes time to plan deep observations across radio, optical, ultraviolet, X-ray, and gamma-ray bands. What might telescopes actually see? The answer depends heavily on whether the merging black holes are surrounded by gas. If the galactic center is gas-rich, the kind of environment where active galactic nuclei, AGN, and quasars live, then there will likely be a circumbinary disk. That disk could respond to the binary in several observable ways. Before merger, the binary can modulate accretion flows, producing periodic variability in the light output as gas streams preferentially feed one black hole or the other. These modulations could show up as repeating dips or peaks in optical or X-ray brightness, potentially identifiable in long-term monitoring surveys. In the final months, as the in-spiral accelerates, accretion rates may fluctuate more wildly. Flickers, flares, and changes in spectral shape could give clear electromagnetic clues that something dramatic is about to happen. At the moment of merger itself, if enough gas is close in, shocks can form when streams collide, or when gas suddenly feels the changed gravity of the newly formed black hole. Those shocks heat the gas and can produce a quick flare, a sudden burst of light, potentially detectable in X-rays or ultraviolet. The flare might be brief relative to human timescales, but because gravitational wave detectors like LISA give a precise merger time, telescopes can watch the target region at the expected moment and catch the flash. If a jet is present before the merger, a relativistic outflow powered by a spinning black hole, the merger can change the black hole's spin direction or power output, causing the jet to brighten, wobble, or switch off. Radio telescopes and X-ray observatories could spot such behavior, but not all mergers will be luminous. Many galactic centers are gas-poor, especially in massive elliptical galaxies where prior activity has already expelled or heated the gas. In those cases, the gravitational waves may be the only direct signal. Still, even a gas-poor merger can leave a trail. Stars kicked out by the binary's interactions create a depleted core in the stellar distribution, a fingerprint that can be found in high-resolution imaging years later. A strong gravitational recoil might also produce an observable signature. A displaced AGN bright emission lines shifted in velocity relative to the galaxy, or a compact cluster of stars traveling through intergalactic space around a wandering black hole. These signatures require careful, sometimes serendipitous observations, but they are part of the suite of clues astronomers use to reconstruct merger histories. There's a delightful interplay between advance warning and fast reaction. LISA-like detectors give the slow, steady approach. Ground and space telescopes bring the rapid response observations. Combining those provides not just a richer snapshot, but a movie that follows cause and effect. Gravitational waves tell you when and how two black holes merged, while photons reveal the gas dynamics and electromagnetic consequences. That's the essence of multi-messenger astronomy. You get to ask causal questions. Did the merger trigger a flare? Did the jet reorient? And answer them with coordinated observations. Beyond catching individual events, large-scale surveys are already hunting for signs of binaries earlier in their lives. Astronomers look for periodic variability in quasars, broad emission lines that are shifted or split, suggesting a pair or a recoiling black hole, and spatially separated pairs of AGN in merging galaxies. Some candidates are tantalizing. OJ 287, for example, has a long history of quasi-periodic outbursts that some models interpret as a smaller black hole perturbing the accretion disk of a larger companion. Another example, PG 1000, 300 and 2-102, shows periodic optical variability that could arise from either a binary or from other accretion disk physics. Distinguishing between models is difficult and requires careful multi-wavelength scrutiny and long-term monitoring. These searches are important because they constrain how common binaries are, how they interact with gas, and whether we should expect many electromagnetic counterparts when LISA starts catching mergers. While electromagnetic signals help us see the environment, gravitational waves are pure probes of gravity. The waveform, the precise pattern of amplitude and frequency over time, is a code written by general relativity. By decoding it, physicists can do powerful tests. One clear test is checking whether the waves propagate exactly as Einstein predicted. For example, if gravitons, the hypothetical particles of gravity in some quantum theories, had a tiny mass, gravitational waves of different frequencies would travel at slightly different speeds, producing a dispersion that LISA could measure. So far, ground-based detectors have already placed tight limits on the graviton mass. Space-based observations and PTAs will probe different parts of the spectrum and tighten constraints even more. Another deep test involves the ring-down phase, the vibration of the newborn black hole. Black holes in general relativity have a discrete set of tones or quasi-normal modes, like the natural frequencies of a bell. Those tones depend only on the mass and spin of the black hole. If we can measure more than one mode, we can check whether the measured set is consistent with a single-Kerr black hole, the rotating solution of GR. Any mismatch could hint at exotic alternatives. For instance, objects without true event horizons, modifications of gravity in the strong field regime, or new physics at the Planck scale. Measuring multiple ring-down modes requires very clean, high signal-to-noise detections, which might be possible for the loudest SMBH mergers that LISA will see. The demographics of merging black holes, how many merge, what masses they have, and how their spins are oriented, tell a larger story about cosmic evolution. There are competing ideas for how the very first supermassive black holes formed. One path is light seeds, the remnants of the first generation of stars, which might start at tens to a few hundred solar masses and grow via accretion and mergers over billions of years. Another path is heavy seeds, direct collapse of massive gas clouds that produce black holes of 10^10^6 solar masses early in the universe, providing a head start for rapid growth. Observing the mass distribution and redshift dependence of mergers helps distinguish between these scenarios. If heavy seeds were common early on, LISA should see more high-mass mergers at high redshift than if growth began solely from light seeds. Spin orientations carry memory of a black hole's life. If a black hole grows mostly via steady accretion from a surrounding disk, its spin tends to align with the accretion flow, often leading to high, coherent spins. If growth is dominated by chaotic accretion of small, randomly oriented gas clouds or by mergers, spins can be more random, sometimes even reversed. Measuring spin distributions with gravitational waves gives a fossil record of growth modes. For example, a prevalence of high, aligned spins in merging binaries would support prolonged, coherent accretion. A scatter of misaligned spins would hint at a merger-rich or chaotic accretion past. There are also practical numbers to keep in mind. Predicting merger rates involves galaxy merger rates, the efficiency of pairing and inspiral of the central black holes, and the distribution of gas and star densities in galactic centers. Estimates vary, but for LISA-like sensitivity, the expected detection rate might be anywhere from a few to a few hundred mergers per year, depending on how common certain seed channels and pairing efficiencies are. Pulsar timing arrays, sensitive to very massive binaries at lower frequencies, will likely detect a background from the collective population first and individual loud sources afterwards. The first hint of a gravitational wave background in PTAs was a watershed moment. It suggests that a population of massive binaries is out there, emitting in the nanohertz regime. The work now is to tease out whether that background is truly stochastic, many unresolved binaries blending together, or whether individual sources will rise above the hum and be individually characterized. One of the richer and more subtle aspects of mergers is the interaction with stars, tidal disruptions. Stars that wander too close to a single black hole can be torn apart in a tidal disruption event, TDE, producing bright, short-lived flares as stellar debris falls into the hole. In a binary, the dynamics change. The tidal sphere of influence can be modified, and the rates of TDEs can be enhanced or suppressed depending on the binary's parameters and the surrounding stellar distribution. A binary might also scatter stars onto plunging orbits, increasing the TDE rate around the merger, or it might eject stars entirely, lowering the local density. Observationally, an increased rate of TDEs in a particular galaxy could be an indirect hint of an ongoing or recent black hole interaction. Another environmental actor is dark matter. While dark matter doesn't interact electromagnetically, it does gravitate. The central dark matter density profile of a galaxy, whether it has a steep cusp or a flat core, can affect how efficiently black holes sink and pair. Conversely, binary hardening via stellar ejections can also reduce the central dark matter density, creating cores. Probing the interplay between SMBH mergers and dark matter can inform both galaxy formation and the nature of dark matter itself. Let's explore a concrete, hypothetical scenario to tie these ideas into a narrative you could follow as an observer. Suppose Lisa detects an inspiral whose parameters indicate two black holes of 10·6 and 3 × 10·6 solar masses at a redshift of 1, about 8 billion years ago in look-back time. Over a year, the signal's sky location refines from a wide patch to a region a few square degrees across. Astronomers begin monitoring that patch with wide-field optical surveys, X-ray satellites, and radio arrays. In the months leading to merger, periodic optical variability emerges from an AGN in a galaxy within that patch, hinting at a circumbinary disk. 2 weeks before the merger, X-rays brighten as gas streams plunge closer in. At the predicted merger time, Lisa registers the peak gravitational wave chirp. Simultaneously, X-ray detectors catch a sharp flare and radio telescopes see the jet briefly brighten and then change orientation. Follow-up spectroscopy shows transient emission lines, and over months the disk settles into a new configuration around the merged hole. The combination of gravitational wave mass and spin measurements with electromagnetic host identification and redshift allows a direct distance redshift pairing, a standard siren, adding a data point to cosmological measurements. That scenario, while optimistic, illustrates the wealth of science unlocked by coordinated observation. But not every story will be so tidy. Data analysis itself is a major frontier. Gravitational wave signals are buried in instrument noise, overlapping sources, and instrument systematics. Extracting parameters requires sophisticated modeling and computationally intensive matched filtering or Bayesian inference techniques. For Lisa, the data streams will be rich and complex. Simultaneously, there will be thousands of galactic compact binaries, extreme mass ratio inspirals, smaller objects orbiting massive black holes, and potentially many SMBH mergers at different stages. Separating these signals, characterizing them, and providing accurate, timely alerts to the astronomical community is a tremendous technical challenge. On the electromagnetic side, localizing faint transients in a few square degree patch, especially where there may be many variable sources, demands careful statistical association. Which flare goes with the gravitational wave event? Cross-matching, multi-wavelength timing, and modeling will be needed to make robust identifications. There are also fascinating offshoots of mergers that produce unexpected phenomena. One idea is that a recoiling black hole with a retained accretion disk could carry a unique spectral signature. Broad emission lines that are Doppler shifted relative to the host galaxy, or a compact point source offset from the galactic center. Finding such objects can be difficult but rewarding. They're smoking guns for past mergers. Another is the concept of a hypercompact stellar system, a tight cluster of stars bound to a recoiling black hole that escaped its galaxy. These systems would be faint, compact, and fast-moving, but with careful searches and deep imaging surveys they might be found. On the theoretical side, simulations continue to refine our expectations. Modern simulations couple in-body dynamics for stars, hydrodynamics for gas, magnetohydrodynamics for magnetic fields, and general relativistic effects for the final plunge. This multiphysics approach reveals nuanced behaviors. Gas torques can align spins before merger, magnetic fields can affect jet production and post-merger accretion, and triaxial potentials can replenish the supply of stars on orbits that harden the binary, overcoming the classic final parsec worries. Simulations are also essential for predicting electromagnetic signatures. What light curve and spectral evolution should a circumbinary disk produce during and after merger? What happens to the disk if the remnant receives a large kick? These are active areas of research because observational strategies depend on reliable predictions. One aspect that often surprises people is what doesn't happen. Despite the violence of the merger, the larger-scale structure of the host galaxy typically survives. Planetary systems in the disk of one of the merging galaxies are not likely to be torn apart directly by the central black holes. The distances are simply too vast. Instead, most of the drama is concentrated in the very center. Over longer timescales, however, AGN feedback ignited or changed by the merger can heat or expel gas, altering star formation across significant regions of the galaxy, and thereby changing its long-term evolution. So the merger's influence can be both intensely local and broadly consequential, depending on how energy couples to the galactic gas. Looking ahead, the synergy between different detectors across the gravitational wave spectrum is especially powerful. Ground-based detectors like LIGO and Virgo will continue to probe stellar mass binaries. LISA will open a window on intermediate masses and lighter SMBHs. Pulsar timing arrays cover the heaviest SMBHs at the lowest frequencies. Together, these instruments create a multi-band gravitational wave view, analogous to observing electromagnetic light in radio, optical, and X-rays. A binary could, in principle, be detected first by PTAs in a low-frequency regime decades before merger, later by LISA as it climbs in frequency, and finally by ground-based detectors only for much lighter cases. Multiband observations improve parameter estimation and tests of gravity, and they create extraordinary opportunities for long-lead electromagnetic campaigns. Finally, the human element. Building the instruments, coordinating global observing campaigns, developing models, and training a new generation of astronomers to analyze multi-messenger data is a massive collective enterprise. The science is inherently collaborative and international. It requires patience, decades-long pulsar timing experiments, missions that take years to develop, and boldness in design and ambition. The rewards are correspondingly rich. Not just a few spectacular detections, but a deep, statistical understanding of how the universe's largest black holes grow and shape their surroundings. All of this sets the stage for a period in astronomy where gravitational waves and light together tell a fuller story. Each observed merger will be a chapter in the broader narrative of cosmic structure formation. How the first seeds grew, how galaxies merged and matured, how black holes influence star formation, and how gravity behaves under the most extreme conditions. While much remains uncertain, the exact rates, the typical environments, and the detailed electromagnetic outcomes, the path forward is clear. With a suite of instruments listening across cosmic frequencies and telescopes poised to respond, we're gearing up to witness these titanic unions in a way that was, until recently, purely the realm of theory and imagination. There's another layer to this story that's rich with drama and surprisingly accessible consequences. What happens when nature doesn't give us just 2 black holes but 3, or when a remnant black hole gets kicked so hard it wanders away from the galactic center? Those scenarios aren't rarities in the universe of galaxies that grow by merging. They add wrinkles to the tale and produce distinctive, sometimes spectacular, observational signatures. Start with gravitational recoil, the kick. During a merger, gravitational waves don't always come out perfectly symmetrically. If the two black holes have different masses or their spins point in different directions, the waves carry away net linear momentum, and conservation requires that the newborn black hole recoil in the opposite direction. Think of it like firing a fire hose. The water leaving the nozzle pushes you back. The recoil speed can be surprisingly large. For many typical configurations, the kick is a few hundred kilometers per second, which might be enough to displace the black hole from the center of a small galaxy. But in special configurations, particularly when the spins are large and oriented just so, kicks can reach thousands of kilometers per second, enough for the remnant to escape even a massive galaxy. Why does that matter observationally? First, a displaced or escaping black hole can produce a unique electromagnetic fingerprint. If the black hole was actively accreting before the merger, that is, surrounded by a bright accretion disk, it can carry with it an inner cocoon of gas and the stars most tightly bound to it. That bound material will continue to emit light as it accretes, even as the hole moves away from the galactic center. To a telescope, you might see a bright point source that's offset from the galaxy's nucleus or emission lines, the spectral fingerprints of rapidly moving gas that are shifted relative to the galaxy's rest frame. Observers have hunted for such displaced AGN and velocity-shifted lines. A few candidates turn up in large spectroscopic surveys, though confirming that a particular source is a kicked remnant rather than, say, a binary with projection effects or an outflow can be tricky. A kick can also set the remnant oscillating through the galaxy. If the speed is below escape velocity but significant, the black hole will slosh through the dense central regions like a bell jar wobbling on a table. Each passage through the dense gas and stars stirs the environment and can trigger repeated flares or enhanced accretion episodes. Over tens to hundreds of millions of years, dynamical friction damps the oscillation, and the black hole settles back toward the center. Those oscillations and any associated off-center activity leave clues in the stellar motion patterns and in the history of central star formation that astronomers can, in principle, read. Triple interactions are another wild card. Galaxies merge often enough that a third black hole can arrive before a previous binary has coalesced. When three massive objects interact gravitationally, the dynamics become chaotic and highly efficient at producing surprises. A common outcome is that the lightest of the three will be ejected at high speed, while the remaining pair hardens. In other words, triple encounters can accelerate binary mergers and produce high-velocity black holes. This is one avenue by which galaxies can end up devoid of a central supermassive black hole, at least for a while, or end up with a wandering intergalactic black hole. Triples also tilt spins and orbital planes in unpredictable ways, imprinting complexity on subsequent gravitational wave signals and on electromagnetic behavior. Observationally, triple-driven dynamics might explain some peculiar AGN and compact stellar systems found well away from galaxy centers. Another subject worth unpacking is how repeated mergers change the character of black holes across cosmic time. A single merger changes mass and spin in predictable ways, but a succession of mergers, hierarchical growth, produces a population with its own statistical fingerprints. If a black hole gains mass mostly through mergers with other holes of comparable size, its spin evolution will look different than if it grew mostly by accreting gas from a disk. Mergers tend to randomize spin directions, and depending on mass ratios, can spin a hole up or down. Coherent accretion from a long-lived disk, by contrast, tends to align angular momentum and spin the hole up steadily. The observed distribution of spins in merging binaries, once we have enough gravitational wave events to build statistics, will tell us which growth pathways dominated in different epochs of the universe. Spin itself plays a practical role in shaping electromagnetic behavior after a merger. A spinning black hole can power relativistic jets, narrow beams of particles, and magnetic fields launched near the event horizon. The efficiency of jet launching depends on the spin, and on how magnetic fields thread the whole. A merger that changes the spin magnitude or tilts the spin axis can therefore change a jet's luminosity and direction. Astrophysicists have proposed that sudden changes in jet orientation might explain some of the peculiar radio morphologies we see, X-shaped radio galaxies, for example, where two sets of lobes suggest a reorientation of the jet axis in the past. A black hole merger that flips the spin axis could naturally account for the creation of a second, differently aligned set of lobes. If you're interested in tests of fundamental physics, mergers are a direct line into strong field gravity. The idea of black hole spectroscopy is simple in principle. The ringdom, the last phase after the horizons have merged, is dominated by a set of quasi-normal modes, discrete tones analogous to the overtones of a bell. In general relativity, those tones depend only on two numbers, mass and spin. If we can measure two or more of those tones independently, we can check for consistency. A mismatch could mean the object is not a Kerr black hole, the solution for a spinning black hole in GR, or it could hint at modifications of GR in the strong field regime. Practically, measuring multiple ringdom modes requires high signal-to-noise ratios, because the higher overtones are faint and decay quickly. The loudest mergers that LISA will detect, those relatively nearby and with favorable orientations, might provide precisely the data needed for this kind of test. Even failing to detect discrepancies is a powerful confirmation of Einstein's theory under extreme conditions. A related experimental angle involves the speed and dispersion of gravitational waves. If gravitational waves traveled at slightly different speeds depending on frequency, which some alternative gravity theories allow, we could detect that by comparing arrivals across bands or by measuring waveform distortions. Ground-based detectors already constrain deviations tightly for the frequencies they probe. LISA and PTAs will probe other portions of the spectrum, extending the reach of these tests to much larger masses and to waves that traverse different cosmic distances. The complementary frequency coverage matters. If some new physics affects low-frequency waves more strongly, or if propagation effects accumulate over long travel times, PTAs could be more sensitive than ground-based instruments. Small companions orbiting massive black holes offer another class of dramatic signals called extreme mass ratio inspirals, or EMRIs. Imagine a stellar mass black hole or neutron star captured into a tight, eccentric orbit around a supermassive black hole. The small object spends thousands of orbits deep in the strong gravity near the SMBH before plunging in, and during that time, it slowly loses energy to gravitational waves. Those waves are rich with information. Because the small object samples many parts of the spacetime, the waveform encodes a detailed map of the central gravitational potential. LISA is expected to detect EMRIs from nearby galaxies, and each detection would allow precise measurements of the SMBH mass and spin, and an exquisite test of whether its spacetime matches the Kerr solution. EMRIs are challenging because their waveforms are complex and long-lived, but they're among the best tools for doing spacetime cartography around black holes. While we're on the topic of signals, it's useful to think carefully about the stochastic gravitational wave background that pulsar timing arrays are starting to hear hints of. That background is the superposition of many unresolved binaries across the universe, each contributing a tiny, slowly varying perturbation to the timing of pulsar signals. The overall hum should have a spectral shape that depends on how binaries evolve and on processes like gas-driven inspiral or coupling to stellar environments. If most binaries evolve purely under gravitational radiation, theory predicts a characteristic power law slope for the background. Deviations from that slope, for example, a turnover at low frequencies, could indicate other physics at play, like interactions with stars or gas accelerating the inspiral, or a different merger rate history. As PTA datasets grow and more pulsars are added, the background will be characterized more precisely, and individual particularly loud sources may emerge from the hum. This leads to another important concept. Environmental coupling. Earlier I mentioned dynamical friction, stellar slingshots, and gas torques as mechanisms that bring black holes together. Those same interactions can leave imprints on the gravitational wave signal. For instance, if gas torques still play a role in the late inspiral for some systems, the gravitational waveform would deviate subtly from the vacuum prediction. Detecting such deviations is hard, but not impossible. If we observe a merger both in gravitational waves and in electromagnetic light, modeling the gas emission together with the gravitational data could reveal the degree to which the merger was gas-influenced. Detecting environmental effects would teach us about densities and temperatures in galactic centers at scales otherwise impossible to probe. Data analysis and alerts are practical but crucial parts of this science. Long before LISA flies, scientists are designing pipelines that can sift through continuous streams of data, separate overlapping signals, and issue alerts with sky locations of promising candidates. The promise of multi-messenger science relies on sending those alerts early enough, and with small enough sky patches that telescopes can point and catch electromagnetic counterparts. For LISA sources, months to years of lead time for some binaries makes that feasible. Telescopes can schedule observations, and transient and survey instruments can be prepared. For PTA detections, where signals evolve slowly, there's a different cadence. Decades-long monitoring is already underway, and any resolved individual source will likely be tracked over many years, giving astronomers time to coordinate deep follow-up. Speaking of follow-up, the electromagnetic landscape is broad. Optical surveys like the Vera Rubin Observatory will monitor large areas of sky nightly, catching variability and transients. Radio arrays like the Square Kilometer Array will map jets and compact radio sources with unprecedented sensitivity. X-ray missions will probe hot gas and inner accretion flows. And infrared telescopes will peer through dust in galactic centers. No single band is sufficient. A classic counterpart might appear as an optical flare accompanied by an X-ray signature, and later a radio afterglow as shocks expand. The more wavelengths you cover, the more complete the physical picture you can reconstruct. That's why the community is designing coordinated observing strategies that include space and ground facilities across the spectrum. There are also practical things we should expect to learn quantitatively once we have lots of data. One is the merger rate as a function of redshift and mass. How common were SMBH mergers when the universe was young versus today? That rate connects directly to how early black holes formed and how quickly they grew. Another is the typical mass ratio. Do most mergers involve roughly equal mass partners, or are they dominated by one big hole cannibalizing a much smaller one? That affects how much mass is radiated in gravitational waves and how often substantial recoils occur. Spin distributions, as I've emphasized, encode growth histories. Environmental indicators tell us about typical gas fractions in the centers of galaxies at different times. All of these measurements will feed back into models of galaxy formation and evolution, constraining parameters that are currently uncertain. Let's put some timeframes around the observational prospects, since that helps ground the excitement in reality. Pulsar timing arrays are already producing tantalizing results. Over the next few years, as more pulsars are timed with higher precision and longer baselines, the background signal should be characterized more definitively, and individual sources may be detected. LISA is scheduled for launch in the 2030s and will open up the millihertz band where many SMBH mergers and EMRIs live. Complementary ground-based missions and next-generation telescopes, like the extremely large telescope, Athena for X-rays, and the NG-VLA for radio, will be in place or coming online in that same general era, allowing detailed electromagnetic follow-up. So while some mysteries will be resolved soon via PTAs, a fuller multi-messenger picture will build over the next decade and beyond as new instruments come online. Not everything is straightforward, and skepticism is healthy. Many candidate electromagnetic signatures can be produced by non-merger processes. variability in accretion disks, jet instabilities, or supernovae in dense environments can mimic some expected signatures. That's why multi-messenger confirmation is so powerful. A gravitational wave detection pins down the merger time and basic parameters, greatly reducing ambiguity. Likewise, interpreting a gravitational wave spectrum in the context of environment or modified gravity requires careful modeling and control of systematics. For some of the boldest tests, like hunting for deviations from GR, the strongest statements will come only after many detections and careful statistical analysis. There are also intriguing possibilities for citizen science and public engagement. Wide-field optical surveys and radio transient searches generate huge datasets where machine learning and human classifiers work together to spot unusual events. The community is already exploring platforms where amateur astronomers, students, and citizen scientists can help classify light curves, search for displaced AGN, or vet transient candidates that might correspond to gravitational wave alerts. That's not just outreach, it's practical. The volume of data coming from next-generation surveys will be enormous, and harnessing distributed attention is both efficient and inspiring. A few real-world candidate systems deserve a quick mention as concrete touchstones. OJ-287, the blazar with a very regular outburst pattern, has long been modeled as a binary, where a smaller black hole pierces the accretion disk of a larger companion, producing outbursts roughly every 12 years. The system's behavior has been used to test general relativity in a different regime, though some details remain debated. PG 1302-102, another quasar showing periodic variability, has been proposed as a binary candidate as well, though alternative explanations involving disk instabilities exist. These systems show how messy the interpretation can be. Multiple plausible models can often explain the same data, and multi-messenger confirmation would be decisive. The theory and simulation side continues to move fast. Increasingly realistic simulations include not just gravity, but gas physics, magnetic fields, radiation transport, and even chemical evolution. These models predict how accretion disks respond to a coalescence, how jets might be switched on or off, and how observable signatures, light curves, and spectra evolve in time. Simulations also help define what kinds of telescopes and observing strategies are best suited to catching the signals. In many ways, observations and simulations are in a feedback loop. Discoveries refine simulations, which then predict new observables for campaigns to test. Finally, there's a philosophical shift worth noting. For much of the history of astronomy, we could only passively observe what the universe happened to show us. With gravitational waves and coordinated electromagnetic follow-up, we're moving toward an active, predictive science of extreme events. We can forecast a merger months in advance with LISA-like sensitivity, plan the coverage, and watch a cosmic experiment unfold in real time. That changes not just the pace of discovery, but the nature of what we can learn. Rather than being limited to after-the-fact detective work, we can design observations that test specific causal hypotheses about how mergers affect surrounding matter, how jets respond, and how gravity manifests under extreme conditions. So many threads are now coming together. Theoretical modeling, improved pulsar timing, the development of space-based interferometers, and the deployment of powerful telescopes across the electromagnetic spectrum. Each merger we detect, whether whispered through the steady cadence of pulsar timing, chirped through LISA's triangular laser arms, or caught as a flare in some distant galaxy, will teach us something new about how the universe builds and sculpts its most massive objects. These events are not only spectacular endpoints of long dynamical journeys, they're also laboratories where gravity, gas, stars, and cosmic history leave combined imprints that we can read with ever-growing precision. If you step back and think about the big-picture questions that come out of all this, they're surprisingly concrete. How did the first supermassive black holes form so fast after the Big Bang? How common are mergers at different cosmic times? How do mergers change galaxies? and what unexpected signals might be hiding in the noise, waiting for instruments to get sensitive enough. Those are the kinds of questions that will get sharper as we gather more data, but answering them means wrestling with messy astrophysical details. Gas and magnetic fields, the motions of stars, and the way general relativity kicks in at the very last moments. Let's unpack some of those details and show why each one matters for what we'll actually observe. Start with the question of seeds and early growth. Observations show quasars, luminous, actively accreting supermassive black holes, already in place less than 1 billion years after the Big Bang. Building a billion solar mass black hole that quickly is hard to explain if you start only with the small remnants of the first stars. Two broad ideas try to fix the problem. One says seeds were light, tens to hundreds of solar masses, but grew extremely fast via very efficient accretion, perhaps in short super-Eddington bursts. The other says some seeds were heavy, direct collapse of massive gas clouds forming 10-4-10-6 solar mass black holes early on. How can gravitational wave detections help? If heavy seeds were common, LISA should see relatively massive mergers at very high redshift. If light seeds dominated, the early merger population would be shifted to lower masses and might require more time to build up. The mass and redshift distribution of mergers is therefore a direct probe of early black hole formation channels. Spin measurements tell a complementary story. Spin is like a memory of how a black hole grew. Coherent accretion, gas falling in with one steady orientation, tends to spin a hole up and align its axis. Repeated random mergers or chaotic accretion events tend to produce a scatter of spin directions and more modest spin magnitudes. Gravitational waves encode spin in the waveform, in the way the orbit precesses, and in the final ringdown. Over many detections, the statistical distribution of spins will reveal whether black holes mostly grew by eating gas smoothly for long stretches, or by gobbling other black holes and chaotic clouds. That in turn feeds back into galaxy formation models, whether feedback from AGN was a steady regulator or a more sporadic, merger-driven affair. The environment around the binary matters for both gravitational and electromagnetic signals. If a lot of dense gas is present in the central region, the binary could be embedded in a massive circumbinary disk. Gas exerts torques, can align spins with the orbital plane to some degree, and can carry away angular momentum in ways that alter the orbit's evolution. This changes the detailed phasing of the gravitational wave signal compared with a purely vacuum inspiral. Detecting those subtle deviations would be like eavesdropping on the binary's neighborhood. A direct probe of gas density and dynamics on scales we cannot image any other way. On the electromagnetic side, a gas-rich environment raises the prospects of clear, observable counterparts, periodic optical variability before merger, flares at coalescence, and an afterglow as the disk resettles. If the environment is gas-poor, the story is different but still rich. Stellar interactions dominate and we get core scouring. Binaries eject stars via three-body interactions, creating the shallow central stellar profiles, cores, we see in many giant elliptical galaxies today. Measuring the size of those cores and comparing them with models tells us how many past mergers a galaxy likely experienced and how energetic those mergers were. In a sense, the stellar distribution becomes a geological record of past black hole archaeology, scars left by repeated central black hole encounters. Now consider the observational endgame, how astronomers will actually find and associate electromagnetic counterparts to gravitational wave events. For ELISA detection, you often get months to years of warning as the inspiral sweeps through the millihertz band. Over that time, the sky localization improves. It might start out as a region tens to hundreds of square degrees and shrink eventually to a handful of square degrees or better. Large area surveys, optical ones like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSSD, will have nightly data over large fractions of the sky, so they're well suited to monitoring candidate regions for variability. X-ray observatories can look for inner disk activity, radio arrays for jet behavior, and infrared telescopes for dust-obscured flares. The practical challenge is that a single few square degree patch can contain thousands of galaxies and numerous variable sources. To pick out the right counterpart, astronomers use a combination of timing. Did something brighten at the time of the merger? Spectral changes, did emission lines shift or broaden? And prior knowledge, is there a known AGN in the patch whose variability matches expectations? Identifying hosts can be statistical rather than unique in some cases. If the gravitational wave localization isn't pin-sharp, the team might associate a merger with one or more likely host galaxies by combining galaxy catalogs, the measured distance from the gravitational wave signal, and models of which galaxies are likely to host massive black holes. That's where large, deep galaxy catalogs become crucial. The better our maps of the local and distant universe, the better we can pair a gravitational wave event with its galaxy. When a unique host is identified, that's a treasure trove. The galaxy's redshift fixes the distance redshift link for the standard siren cosmology measurements I mentioned earlier. There's also a lot of nuance in the timing of electromagnetic signals. Some models predict a precursor, a gradual brightening or periodic modulation in the months or years leading up to merger as gas interacts with the evolving binary. Some predict an immediate flare as gas shocks when the potential suddenly changes at merger. Others predict a delayed afterglow. The merged hole might be kicked or might change its spin, and only later restart accretion as material falls back in, creating a flare months to years afterwards. A careful, multi-epoch observing campaign can test these scenarios, but it requires patience and coordination. Beyond straightforward flares, some of the most interesting observable consequences are morphological. A merger that reorients the black hole's spin axis could reorient any jets it was producing. Over timescales of tens of thousands to millions of years, that jet reorientation shows up as double or X-shaped radio lobes, or in other complex radio morphologies. Observers have found galaxies exhibiting these features, and while a merger is not the only explanation, it's a natural one. If Lisa ties a more recent merger to a galaxy that later shows jet reorientation, that's a smoking gun linking the dynamics near the horizon to galaxy-scale radio structures. Let's look more closely at some of the more exotic or subtle signatures that could come out of mergers, the ones that would be both surprising and scientifically transformative if found. One is gravitational wave memory. Most gravitational waves oscillate and pass, leaving space stretched and compressed and then relaxed again. But some portion of the wave can produce a tiny permanent change in the relative separation of distant test particles. A memory effect. Detecting this would be a novel test of general relativity's nonlinear nature, and pulsar timing arrays are one of the places where memory might be measurable because memory accumulates and affects pulse arrival times in a permanent offset-like way. Measuring memory would provide a direct window into the non-oscillatory aspects of gravitational wave production. Another subtlety is gravitational wave lensing. Just like light, gravitational waves can be lensed by massive structures between source and observer. Lensing can magnify a gravitational wave signal, change its apparent distance, or produce multiple images that arrive separated by days to years, depending on the lens geometry. In principle, a lensed gravitational wave event would look brighter than expected for its estimated redshift, and could produce repeated, similar waveforms separated by the lensing time delay. Detecting lensing of gravitational waves could help map intervening mass distributions and open up a new way of doing lensing science with waves that are not affected by dust or scattering. Dark matter plays multiple roles in this story. Dense spikes of dark matter could, in principle, form around black holes, and their presence or destruction would affect both the dynamics and potential electromagnetic signals near the center. If dark matter annihilates into standard particles, a dense spike could, in theory, create a gamma-ray signal, but mergers tend to flatten and disrupt central dark matter concentrations, so the presence or absence of such signals is an indirect clue to the interplay between black hole dynamics and dark matter physics. More generally, the shape of the central dark matter and stellar potential affects how quickly black holes sink and pair. Triaxial or lumpy potentials help replenish the supply of stars that can interact with the binary, resolving the classic final parsec concern in many cases. Triples and higher-order multiples are another area where nature can surprise us. If a galaxy merger introduces a third black hole before a binary has finished coalescing, the three-body problem often leads to chaotic outcomes. Ejections of one black hole at high speed, accelerated merger of the remaining pair, or complicated exchanges and flips of spin orientation. Triple interactions can both speed up mergers and produce a population of fast, wandering black holes. From an observational point of view, triples complicate gravitational wave waveforms and increase the diversity of possible electromagnetic signatures. They also increase the likelihood that a galaxy may, at times, lack a central black hole because it was ejected by a dynamical interaction. What about neutrinos and cosmic rays? Most models of SMBH mergers don't expect strong neutrino emission because gravitational wave-driven mergers don't naturally produce the dense, hadronic shocks that efficiently make high-energy neutrinos. But if a merger occurs in a particularly dense, magnetized environment, say, with a thick accretion flow or a disrupted star supplying dense gas, it's conceivable that shocks could accelerate particles and produce high-energy neutrinos or cosmic rays. Detecting neutrinos coincident with a merger would be very surprising and would immediately tell us the merger happened in an especially extreme electromagnetic environment. It's an area where theory is still speculative, but detectors like IceCube and future neutrino observatories will be paying attention. Let's return to the practical machinery behind extracting physics from gravitational waves. Numerical relativity, solving Einstein's equations numerically on supercomputers, was essential to even know what a binary black hole merger wave looks like in detail. Those simulations are computationally expensive, and for LISA and PTA science, we need extensive libraries of waveforms covering wide ranges of masses, mass ratios, spins, and orbital elements. To make data analysis feasible, theorists build approximate models, waveform families, calibrated to full numerical simulations. There are also growing efforts to use machine learning and surrogate modeling to produce accurate waveforms quickly. These computational tools are the backbone of matched filter searches and parameter estimation pipelines that turn raw detector data into physical measurements of mass, spin, distance, and sky location. Data analysis faces many unique challenges in the low-frequency regime. For LISA, the data stream is continuous and contains overlapping signals from many sources, millions of galactic binaries in our own galaxy alone, EMRIs, and possibly dozens of SMBH inspirals. Separating this signal soup requires sophisticated source separation techniques. For pulsar timing arrays, the major challenge is long-term stability. Pulsars must be timed for many years with exquisite precision, and one must control for a host of astrophysical and instrumental noise sources. For both methods, international collaboration, data sharing, and open methods will be crucial to reach robust conclusions. Now imagine a concrete example to illustrate how all these pieces come together. Think about the eventual merger of the Milky Way's central black hole, Sagittarius A, roughly 4 million solar masses, with the black hole at the center of the Andromeda Galaxy, which will happen as the galaxies merge many billions of years from now. In that remote future, the merger of the two galaxies' central black holes could follow the narrative we've discussed. Dynamical friction brings them together. Stellar interactions and gas torques harden the binary, gravitational waves take over in the final stages, and the merged black hole leaves imprints on the host galaxy. For us now, this is a useful thought experiment. It gives scale. Sagittarius A is small compared with the billion solar mass monsters in giant ellipticals, so its gravitational wave signals would be in a different frequency band and would probably be more amenable to LISA-like detection if such an event occurred within the right distance. The key takeaway is that similar physics plays out over a huge range of masses, and by observing events across that range, we learn the underlying rules that govern them all. One of the most practical and potentially revolutionary uses of SMBH mergers is in cosmology. Gravitational wave sources act as standard sirens. The waveform gives you a direct handle on the luminosity distance to the source without relying on the cosmic distance ladder used in electromagnetic astronomy. If you can associate the gravitational wave event with a specific host galaxy, and therefore measure its redshift, you can place a point on the distance-redshift relation. Doing this for many sources gives an independent measurement of the expansion rate of the universe and other cosmological parameters. That's particularly valuable given the current tension in measured values of the Hubble constant between the local distance ladder and the cosmic microwave background determinations. SMBH mergers offer another, completely independent path to pin down those numbers. There's also potential for surprising discoveries that challenge established physics. Mergers probe gravity in regimes that are otherwise impossible to reach. Highly dynamical, strong-field systems where spacetime is being violently reshaped. If any deviation from general relativity exists at astrophysical scales, merging black holes are where it might show up first. Tests span a range, checking that gravitational waves of different polarizations behave as predicted, looking for dispersion that would indicate a massive graviton, measuring the Ringdon modes to test the no-hair theorem, and searching for echoes or persistent deviations that might hint at exotic alternatives to black holes, like certain horizonless objects proposed in speculative theories. So far, ground-based observations of stellar mass black hole mergers have been consistent with general relativity. But SMBH mergers probe different masses, longer wavelengths, and a different set of physical conditions, so they expand the range of theories we can test. We should also circle back to the human and technical infrastructure that will make all this possible. Building instruments like LISA, 3 spacecraft flying in a triangular formation millions of kilometers apart, maintaining picometer-level distance stability with laser interferometry, is a massive engineering endeavor. So is running long-term pulsar timing campaigns across continents, building radio arrays like the Square Kilometer Array, and operating large optical, infrared, and X-ray facilities that can follow up alerts. All these efforts are coordinated internationally and require software systems for rapid alerts, data sharing, and joint analysis. The community is already planning multi-messenger networks and protocols to ensure rapid communication, so telescopes can respond within hours or days to a predicted merger. That kind of orchestration is new at this scale for astronomy and mirrors, what has already worked well in the transient sky for stellar mass gravitational wave events and gamma-ray bursts. Machine learning and citizen science will both play a role. Machine learning helps sift through the stupendous data volumes, finding candidate variable sources in time-domain surveys, classifying light curves, and helping denoise gravitational wave datasets. Citizen science projects can harness human pattern recognition to vet candidates where an automated pipeline is uncertain, or to find uncommon patterns that algorithms might miss. Both approaches are complementary. Humans are great at seeing oddities and contextual clues, while machines excel at scaling to petabytes of data. As the data arrive, the community will be building catalogs rather than single blockbuster detections. Each catalog entry is a data point that informs population statistics, how often certain mass ranges merge, what the distribution of mass ratios is, how spin orientations appear, and those statistics, in turn, refine our theoretical models. It's a virtuous cycle. Observations inform models. Models make predictions for future observables. Instruments are optimized to test them, and the next generation of observations tightens constraints further. Finally, it's worth acknowledging the role of serendipity. In many past astronomical discoveries, the most exciting findings were not the ones that were predicted most loudly, but the unexpected anomalies that forced us to rethink assumptions. As LISA and PTAs push into new regimes, and as large-scale surveys watch parts of the sky constantly, the probability of unexpected phenomena increases. Maybe a merger will occur in a gas environment unlike any modeled so far, producing a novel electromagnetic signature. Maybe a particularly strong recoil will eject a black hole and its entourage of stars in a way that's detectable as a hypercompact stellar system. Maybe a lensed gravitational wave signal will arrive with a twin and allow us to map an intervening galaxy cluster in a new way. Astronomy is, as always, a mix of the predictable and the surprising, and the study of supermassive black hole mergers sits right at that intersection. There's still a lot we don't know. The exact rates and mass distributions of mergers, the typical gas fractions in galactic centers at different epochs, how often triples form, and how frequently mergers produce bright electromagnetic counterparts. But each of those unknowns is a measurable quantity. Over the next decades, as pulsar timing arrays mature, LISA flies, and next-generation telescopes come online, these measurements will become routine. That will move the subject from speculative and theoretical to empirical and detailed, turning single dramatic narratives into comprehensive science about how black holes and galaxies co-evolve across cosmic time. One last practical point before we move on. The way we interpret observations will always be model-dependent to some degree. A measured flare could be from a merger or from some disk instability unrelated to any binary. A periodic signal could be a binary or could be produced by processing disk features. Robust science will require not just single detections, but converging lines of evidence, consistent gravitational wave parameters, electromagnetic timing, and spectral behavior that match physical expectations, and follow-up observations that rule out competing explanations. That's why multi-messenger observations are so powerful. They let you cross-check and triangulate the physical scenario from independent channels. With all of these avenues, observational, theoretical, computational, converging, the study of supermassive black hole mergers is poised to be one of the most productive areas in astrophysics. We're building the tools to both predict and watch these cosmic unions in real time, and we're developing the data analysis machinery to extract deep physics from messy, overlapping signals. The coming years promise to convert the many theoretical possibilities I've described into a robust empirical picture. Which channels of growth dominate for black holes, how mergers influence galaxies, how frequently kicks produce wandering holes, and whether general relativity continues to pass precision tests in regimes it has never been tested before. That picture will be multifaceted. It will be painted by gravitational waves heard as long, low-frequency hums or short, sharp chirps, by optical and X-ray flares, and by radio jets that change direction, by stellar cores that remember painful ejections, and by population statistics that tell the tale of hierarchical assembly. It will require careful comparison between simulations that include gravity, gas, magnetic fields, and radiation, and observations that span the electromagnetic spectrum and stretch across time and space. And because every detection informs the next, the field will grow quickly from a handful of intriguing candidates to a dense network of events that trace the cosmic history of black holes and galaxies. We've sketched the broad drama and some of the science, but there's a next level of detail that ties the predictions to what we will actually measure and how we'll interpret it. Let's get a little more specific about the signals, the ways we'll catch them, and the sorts of discoveries that could change the way we think about black holes and the galaxies that host them. First, the sound and scale of the signal. Gravitational waves are tiny changes in distance. A passing wave stretches and squeezes space by a fraction so small you need extremely sensitive instruments to detect it. How small? For typical supermassive black hole binaries that LISA will see, the fractional change in length, called strain, can be on the order of 10⁻17 to 10⁻20 by the time the waves reach us, depending on the masses and the distance. Those numbers are minuscule, but they're exactly the sort of tiny wiggles that laser interferometers in space are designed to pick up. because the effect builds up coherently over millions of laser cycles, and because the instruments measure differences across arms millions of kilometers long. Pulsar timing arrays, on the other hand, don't measure changes in distance directly. They measure changes in the arrival times of radio pulses from millisecond pulsars. The signature of a nanohertz gravitational wave is a correlated pattern of tiny timing deviations across many pulsars, nanoseconds to tens of nanoseconds over years. And that's the kind of precision current PTA efforts are approaching. Frequency gives a simple way to sort the different kinds of mergers. Roughly speaking, heavier systems produce lower frequency waves. Stellar mass black holes that LIGO detects sit in the tens to hundreds of hertz range. Supermassive black holes live at much lower frequencies. A pair of 1 million solar mass black holes in their final inspiral would sweep through a millihertz band, right in LISA's sweet spot, over months to years. A pair of billion solar mass holes has orbital periods of years to centuries in their late stages, and produces nanohertz waves that PTAs are sensitive to. That inverse relationship between mass and frequency is one reason a range of detectors across the gravitational wave spectrum is so powerful. Each detector hears a different part of the black hole population. How long will you be able to watch a given system? That depends on its mass and how soon you start listening. For LISA, some binaries will enter the instrument's band months to years before merger, allowing extended monitoring that refines parameters like mass, spin, and sky position as time goes on. That's game-changing because it turns a single-time transient into a prolonged campaign. You can prepare telescopes, plan coordinated observations, and watch the environment respond leading up to, during, and after the merger. PTAs, meanwhile, don't usually give a countdown clock in the same way because the timescales are so long, years to centuries. But as the timing baselines lengthen, individual massive binaries may be pulled out of the stochastic background and tracked across years. When LISA watches a binary over months, its sky localization improves steadily. Early on, you might only know the source is somewhere within tens or hundreds of square degrees, but as the chirp grows, you can often narrow that down to a few square degrees or less. That's still a lot of real estate on the sky. A few square degrees can contain thousands of galaxies, but it's manageable with coordinated observing plans. Telescopes with wide fields of view, like Rubin Observatory, will be crucial to monitor those regions for variability, while narrow-field, high-resolution instruments will be used to study any particularly promising candidates in depth. Now let's look at the kinds of electromagnetic signatures you might see and when to expect them. The most promising environment for a bright counterpart is a gas-rich galactic center with a circumbinary disk. Before merger, that disk is often expected to develop a central cavity carved out by the binary's orbit, with streams of gas crossing the cavity to feed mini-disks around each black hole. Those streams and mini-disks can cause periodic modulations in brightness as the feeding rate shifts with the orbital phase. Observers might see quasi-periodic oscillations in optical and X-ray light prior to merger, a kind of heartbeat that hints at a binary. In the final stages, as the inspiral accelerates, the mini-disks may experience more violent fluctuations. At merger, some models predict a prompt flare when gas in the inner regions shocks as the potential changes suddenly, and as the remnant ringdome redistributes energy. The flare could be primarily X-ray or ultraviolet, but depending on obscuration and column density of gas and dust, it may show up in optical or infrared bands as well. After the merger, the remnant black hole can receive a recoil kick. If the kick is modest, the hole will oscillate through the central region, stirring gas and producing episodes of enhanced accretion each time it passes through higher density regions. This can lead to repeated flaring over tens to hundreds of millions of years. If the kick is large enough for the hole to escape or to travel far from the galactic center, you could see a bright, offset AGN, a luminous point source that doesn't match the galaxy's center, or emission lines significantly shifted in velocity relative to the host galaxy. The observable manifestation depends on how much gas the hole carries with it, A hole with a dense mini-disk in tow will keep shining for longer, while a naked remnant will fade quickly. Not every event will be electromagnetically loud. In gas-poor, dry mergers, typical of massive ellipticals that have been quenched of star formation, there may be little gas to light up. In those cases, the gravitational waves themselves are the cleanest signal, and the galactic center may instead show structural scars. A depleted stellar core where past binary interactions ejected stars. That means some mergers will be best studied by their gravitational waves and their long-term structural fingerprints rather than by immediate light. As we go from the qualitative to the quantitative, event rates and detection yields matter. Predicting how many mergers an instrument will see is one of the reasons people build population models of black holes and galaxies. For LISA-like sensitivities, estimates vary but generally range from a few to a few hundred detectable mergers per year, depending on assumptions about how early black holes formed, the seed question. How efficiently galaxies deliver their central black holes to mergers, and how much gas is available to help them harden. For pulsar timing arrays, the expectation was long that a stochastic background from the cosmic ensemble of massive binaries would be the first detection. Now we're seeing tantalizing evidence of that background. The next step for PTAs is to resolve the background into individual loud sources, a handful of very massive, relatively nearby binaries that stand out above the hum. Those will be rare but extremely informative, because a resolved PTA source could come with precise mass estimates and, potentially, identification of a host galaxy. The gravitational wave signal itself encodes rich physics. The inspiral phase teaches you the chirp mass, a particular combination of the two masses, the mass ratio, and hints of spin through precession and phase modulation. The plunge and merger give the most power and allow precise measurement of the final mass and spin of the remnant. The ringtone, the final vibration of the newborn black hole, is a key target for tests of general relativity. In general relativity, the ringtone frequencies and decay times are fixed functions of the remnant's mass and spin. If we can measure more than one quasi-normal mode, multiple notes of the ringing, we can check whether they're all consistent with a Kerr black hole. Deviations would be one of the few direct ways to see beyond the classical black hole picture. That's not just a cool measurement. It's a direct test of the no-hair theorem and of gravity itself in the strongest, most dynamical fields available. Doing that requires high signal-to-noise detections because higher overtones are fainter and die away quickly. LISA's best events could provide that fidelity for SMBH mergers. PTAs and ground-based detectors probe different regimes, so together we span a broad testbed for strong field gravity. Another fundamental test concerns how gravitational waves propagate. If gravity were mediated by a massive particle, or if some modification of gravity caused dispersion, different frequency components of a gravitational wave would arrive at different times from a distant source. Comparing arrival times and phases across bands, or looking for distortions relative to precise waveform models, constrains such scenarios. Ground-based detectors have already placed tight constraints at their frequencies. Space-based and PTA measurements will extend those tests to different masses and distances, broadening the search for subtle deviations. Spin measurements deserve a special call-out because spins are a memory of a black hole's life. If a black hole grows mainly by steady accretion from a disk with a fixed orientation, its spin tends to grow large and align with that disk. If growth occurs through chaotic accretion events or repeated mergers, spin directions become more random and magnitudes can be more modest. By collecting spin measurements from many mergers across cosmic time, astronomers will assemble a story of black hole growth. Whether the early universe favored heavy seeds that grew by mergers, or whether growth was driven by gas accretion, and how those channels changed with redshift. That in turn feeds directly into models of galaxy formation and the evolution of AGN feedback. Speaking of feedback, a merger can change the course of a galaxy. If the remnant black hole accretes rapidly and launches strong winds or relativistic jets, It can heat or remove gas from the galaxy, quenching star formation. On galaxy scales, these effects play a major role in shaping the morphological and color evolution of massive galaxies. If mergers commonly trigger strong AGN episodes, that helps explain why the most massive galaxies in the local universe are typically red and dead. Observations tying the timing of a merger to subsequent AGN activity would provide direct evidence of this causal chain. Let's look at a few vivid hypothetical examples to make this concrete. Imagine Lisa identifies a binary of two 10-6 solar mass black holes at a redshift of about 0.5. Over the course of a year, the sky localization improves from hundreds of square degrees down to a few square degrees, and telescopes begin to monitor the region. Optical surveys note a quasar in that patch displaying periodic brightness variations, matching the binary period inferred from the gravitational waves. 2 days before the predicted merger, X-ray flux increases. At the time of merger, Lisa records the chirp peak and space-based X-ray observatories catch a brief, bright flare. Radio telescopes see the jet momentarily brighten and then shift direction over months. Combining the gravitational wave-derived distance with the host galaxy's spectroscopic redshift gives a point on the distance redshift plot, helping cosmologists refine the expansion rate. Meanwhile, spectroscopic monitoring reveals emission lines briefly shift in a way consistent with a transient recoil. That one event would illuminate gravity, galactic environment, jet physics, and cosmology all at once. Now imagine a different case. PTAs detect a loud nanohertz source that is localized well enough to point deep optical and infrared observations. There's no obvious bright AGN at that location, but high-resolution imaging shows a subtle stellar core deficit, the signature of past scouring by black hole binaries. Radio searches find no persistent jets, but a compact cluster of unusually fast-moving stars is seen a few parsecs away from the galactic center. These observations together suggest a massive remnant that received a strong recoil and dragged a small collection of bound stars out with it. That would be a striking example where the gravitational waves tell you a merger happened, but the electromagnetic signatures are subtle and indirect. Both scenarios highlight something important. Multi-messenger astronomy is rarely a simple one-signal, one-interpretation game. Often you need multiple lines of evidence, timing coincidences, spectral behavior, morphological changes, and statistical association with galaxies to build a robust narrative. That's why coordinated observing strategies and shared data pipelines will be critical. There are technical challenges too. For Lisa, data analysis must deal with a crowded instrument band. Long-lived signals from many binaries, signals from extreme mass ratio inspirals, and foregrounds from galactic compact binaries all overlap. Separating these signals so you can cleanly extract parameters requires sophisticated source separation and Bayesian inference techniques. For PTAs, the primary challenge is stable, long-term timing of many pulsars, controlling for noise sources like spin irregularities, interstellar medium delays, and clock errors. Both approaches demand patience and careful control of systematics, but the first detections already show that those strategies are working. Simulations play a central role in making sense of observations. Modern simulations combine general relativistic gravity, magnetohydrodynamics, radiation transport, and sometimes even chemistry to predict how gas behaves around a binary before, during, and after merger. Those simulations allow theorists to predict light curves, spectral changes, and the structure of jets, and they calibrate waveform models used in data analysis. Advances in computational methods, surrogate models, machine learning emulators, and more efficient GRMHD solvers are making it feasible to explore large parameter spaces and provide the templates required for matched filtering and parameter estimation. Triple systems and recoil dynamics introduce additional richness and unpredictability. If a third black hole arrives at a galactic center before a binary coalesces, the three-body interaction is often chaotic and can produce quick ejections of one black hole and rapid hardening of the remaining pair. Dynamically, this can speed up the production of mergers and produce a population of wandering black holes, or even leave a galaxy temporarily without a central black hole. Observationally, this could explain some off-center AGN and compact stellar systems. Kicks themselves are a numerical relativity success story. Simulations show recoil speeds can range from a few tens to several thousand kilometers per second, depending on mass ratio and spin geometry. A kick of several hundred kilometers per second can displace a black hole within its host. The most extreme kicks, which require fairly special spin arrangements, can eject a black hole into intergalactic space. A curious side effect of recoils and ejections is the fate of bound stars and gas. A black hole that's kicked but retains a tight cluster of stars will look like a hypercompact stellar system moving relative to its host galaxy. These systems are faint and hard to find, but if discovered they would be strong evidence of past dynamical interactions. Similarly, if a black hole escapes entirely, it could, in principle, carry enough gas to continue shining as a wanderer for a while, producing an isolated off-center quasar-like source. On the cosmological front, SMBH mergers offer several unique tools. We mentioned standard sirens, gravitational wave-derived distances that, when matched to redshifts from electromagnetic identification, provide direct measurements of the expansion history of the universe. Because gravitational waves are absolute distance indicators, they don't rely on uncertain calibrations of luminosity. They complement existing techniques and provide an independent cross-check on measurements that currently disagree at some level, such as the Hubble constant tension. The catch is that you need an identified host to get the redshift, which is easier for LISA sources than for most PTA sources, because LISA often gives better sky localization. Still, even a handful of well-localized standard sirens from SMBH mergers could make a valuable contribution to cosmological constraints. There are speculative, high-risk/high-reward possibilities too. If black holes aren't exactly the simple objects general relativity predicts, mergers might produce weak echoes, persistent deviations in the ringdom, or resonances not captured by Kerr quasi-normal modes. While current observations of stellar mass mergers show no clear deviations, the SMBH regime is qualitatively different, and future high signal-to-noise observations could reveal surprises. Other speculative signals include dense dark matter spikes near black holes producing indirect particle signatures, or extremely magnetized environments producing neutrino or cosmic ray emission during a merger. These possibilities are less likely than the core scenarios, but the instruments and multi-messenger networks we're building are sensitive enough that we'll be testing them. What about timelines and what to expect in the next few decades? Pulsar timing arrays have already reached a milestone, a common spectrum process across pulsars that's consistent with the stochastic gravitational wave background. And work is now focused on confirming the quadrupolar spatial correlation, pattern characteristic of gravitational waves, and on teasing out individual loud sources from the background. LISA is scheduled for launch in the 2030s, opening the millihertz band to direct observation. Complementary observatories, large optical surveys, new X-ray missions, next-generation radio telescopes, and extremely large optical/infrared telescopes will be operating or coming online in the same era, making coordinated multi-messenger campaigns possible. So the next 20 years should see a steady stream of new information, from a broad hum detected in pulsars to resolved SMBH inspirals, and in the most optimistic scenarios, joint gravitational wave and electromagnetic detections that narrate a merger from months of inspiral to the ringdom and its aftermath. There's an important human and institutional dimension to this science as well. Multi-messenger success depends on collaboration across traditionally separate communities. Radio astronomers, optical survey teams, high-energy observers, gravitational wave analysts, theorists, and computational modelers. That coordination requires standardized alert protocols, rapid data sharing, and joint observing programs. The good news is that the astrophysics community has been learning these workflows through stellar mass gravitational wave detections and gamma-ray burst follow-ups. Those lessons will scale up for SMBH mergers. Citizen science and machine learning will play supporting roles. Citizen scientists can help vet rare light curves and morphological oddities, while machine learning systems will triage enormous data streams to flag promising candidates for human inspection. Finally, there's a cultural and educational opportunity. These mergers are dramatic stories that capture the public imagination. Two cosmic giants spiraling together, spacetime ringing like a bell, the birth of a mightier black hole, and the ripples of consequence for its host galaxy. Communicating this science broadly, with clear visuals, sonified gravitational wave signals, and accessible narratives about the instruments and people involved, is a chance to bring the excitement of discovery to wide audiences. At the same time, that outreach has a practical benefit. It builds public support for large, long-term scientific projects and inspires the next generation of scientists and engineers who will design the instruments and analyze the data. So what's the upshot? Over the coming decades, we will move from hints and theoretical expectations to detailed, multi-channel observations that reveal how supermassive black holes meet, merge, and remake their environments. Some mergers will be silent in light and loud in waves. Others will be fireworks across the spectrum. Each detection will be a piece of a larger puzzle. How the first black holes grew so fast, how often galaxies merge, how black holes shape galaxies through feedback, and whether anything about gravity itself breaks down in the most extreme settings. The instruments and analysis tools are advancing rapidly, and the early signs from pulsar timing and the steady march towards space-based interferometry tell us we are at the beginning of a new era. One where we won't just discover that two supermassive black holes merged somewhere in the distant universe. We'll be able to tell the story of that merger in detail, watch its aftermath unfold, and use it to answer some of the deepest questions about how the cosmos evolved.